Oh boy. Hello everybody. Welcome back. And I'm gonna eat something, okay, on camera, because I took this very long nap, and after you take a nap, it feels like you know, yeah. I feel like I need to eat something very kind of sweet. It's Mandarin orange, no sugar added. I really like this stuff. I bought it in Walmart. So what was this plant's name? Something o- Otio or something? Let me look it up again. Ocotillo. Okay, that's such a difficult name to remember. Ocotillo. 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 One of the most beautiful plants I've ever seen. Very beautiful plant. Oh, this is good. Ah, this is like taste of paradise, man. Oh boy. And also, yeah, I have this little things in life: ice water. Oh, water tastes good when it's cold, and sugar-free soda pop. Isn't it funny that I call this drink soda pop, diet soda pop? I don't want to advertise any products. Okay. Oh. Oh, so good. Okay. All right. So we are dealing with this moral hierarchy of proton pump, electron pump. The law of anti-entropy. In Wow, what's going on with my hair? Woo! I want to look like a lion. Shoot ass ghetto lion. uh, yeah, there's moral hierarchy of anti entropy. Okay, so uh, so it's kind of like topological concept. Okay, so we are defining direction not to west or east, or up or down, front and back. That's like Cartesian way of thinking, right? Directionality. It doesn't have to be that way. We can define direction in terms of some topological way, set theoretical way, right? So you have some boundary. Doesn't have to be perfect circle. It's just topological circle. Okay, it can be bean shaped or oval. Doesn't matter. Okay. Now, it's a topological direction. Okay, topological directionality. Is it going toward the circle, or is it going out of the circle? Okay, that's what we're talking about. All right. And is it the negative copium? We call it negon. Okay, or is it positive copium? We call it poson. Okay. Yeah, on is like entity unit, Greek origin. Okay. Yeah. So yeah, let's do some mathematics then, okay? All right. You're gonna assign some signs, all right? So something that comes out that's negative, okay? So if some good thing is coming out, it's like this. Minus plus 1 is equal to minus 1. So that's bad, right? If some bad things is coming out of your system, like you defecate, you urinate, you venting out your anger, oh, now I feel good. It's called catharsis, okay? Catharsis. Yeah, something coming out, you are losing something, but you are losing something bad, which is good, okay? Now, something is coming inside, and it's something very good, okay? Okay, so coming in, that's plus, you are obtaining something, and it's something good. Oh, that's very good. But if something bad is coming inside, like some parasite, STD, disease, mosquito, oh, you're obtaining something bad. So result, minus 1, okay? So that's this arithmetic for this anti-entropy theory, okay? Anti-entropy mathematics, okay? If it's coming in, you assign positive this unary operator, okay? Negative, it just flips the sign. So it's called unary operator. A plus B, that kind of plus, that's binary operator, okay? And if there's function that takes in 3 variables, what is it? Ternary operator, okay? Unary, binary, ternary. If it takes 4, maybe quaternary, something like that, okay? So I don't know too much beyond that, okay? I don't know all this Latin and whatnot, Greek. They're beautiful language, but I just don't know much about it, okay? I hope I have time to study those wonderful things, okay? Okay, so yeah, if it's plus, then it's a unary operator that preserves the sign of the number itself, okay? But if unary operator minus, it flips the sign of the number, internal sign, okay? So that's that. And Jesus-Yen way is like, oh, crucifixion, right? So you take in all the bads and you give out all the goods. So it's self-sacrifice, okay? Altruism, all right? That's Jesus-Yen ethics, okay? It's as high as it gets, okay? Now, so one way to look at Jesus-Yen ethics is this. You give away what you have, okay, so that you can receive something new, okay? Like here in humanology, I'm giving you everything I have. I mean, I don't have money, okay, so I cannot give you money, all right? So, but I'm giving you all the knowledge that I have, okay? Everything I know, I'm giving it to you for free, okay? So now my brain is like brain dump, right? I'm dumping all this garbage, junk inside of my brain to you. So you're like a garbage collector, okay? Or you can think of this as gold and diamond, okay? So sure, yeah, that's what Solomon said, right? Yeah, knowledge is better than gold, right? It doesn't look like gold to me. What a metaphysical gold, sure. Okay, I'm giving it to you so that I can. Now my brain is empty because I just did the brain dumping on your head, so that I can get something new from God world. Okay, yeah, let's brain dump so that I learn something new. Now I'm filling my brain with all the new stuff. Okay, okay, all right. Um, so that's that, and Ocotillo and Joshua Tree. This is called Jacob's staff, Ocotillo. That's his nickname. Jacob's staff. Ooh, looks like some kind of bacteria, man. Some shit ass bacteria. Germ. We're gonna take a break, okay? Because I don't know what else to say. We're gonna take a break. Oh boy, I don't know what else to say about that. Yeah. So basically, I just rolled out of my bed, so I'm oh kind of out of it. So, but yeah, we have good mathematics here, okay, for this anti-entropy theory of an organism, okay, or organization, organism. It's same thing, okay, same principle. Macrocosmos, microcosmos, and macrocosmos, okay. Small universe, big universe, okay. The cellular level, organism level, then organizational level, okay. All right, let's take a break from this, okay? So it's like core humanology right here, okay? It has nothing to. Yeah, you can connect this to economics, right? Sure. Economics, the wealth of a nation, like Adam Smith wrote about, okay? Yeah, I took a look at his book, just a few pages, and it's too detail oriented, okay? So I wasn't quite interested in reading it cover to cover. Maybe one day if I have time. But I didn't read it, okay? Because what we do here is we are not looking at the individual trees, okay? Yeah, sometimes when we write a novel, okay, yeah, then kind of we get detail oriented because you're describing what happened, events, character driven kind of novel. Sometimes we do that, right? You do acting here, right here, okay? We write novel sometimes, okay? It's a narrative. Yeah, then we get detail oriented. But when we deal with humanology, we are trying to find big picture, some unifying, governing, higher law that pervades the universe, generic principle. Okay, big picture. That's some we do modeling like this, mathematical modeling, right? Okay, now we are dealing with topology here, right? We define a new directionality. Okay, it's not west or east, but no, is it coming inside of this sphere or coming out of it? Okay, that's the directionality. Okay, see, see. Love that Superman movie. Oh, Superman 3. It was fantastic. Oh boy. So we're gonna take a break from it. Yeah, they say, oh, these natural resources like iron, diamond, gold, are they limited? What's your answer? Will we ever run out of iron, gold, silver, copper, those precious metals? Are we gonna run out of it one day? Do you think so? Or are they renewable resources? Okay, it's a very scientific question, okay? We are not doing politics here, it's science. They are constantly being generated. By whom? Earth, okay? Earth can be thought as this factory. You have this magma, right? So you go deep down in the earth. Yeah, they have this pressure and heat. So yeah, different elements. Okay, you have this periodic table in chemistry, right? Uh, Back in the days in Europe, there's this alchemy, and also in China too. Alchemy. How can we make gold? Okay, is it possible? Yes. Okay, elements, different elements in the periodic table, they're interchangeable. Okay, they can become another element by gaining one more proton, one more neutron, or one more electron. Okay, so they're interchangeable. All right, but it takes a lot of energy, and that's what Earth is doing. Okay, it's constantly converting one element to another element, one atom to another atom. Okay, so yeah, it's like furnace, this manufacturing factory of gold, silver, aluminum, all that stuff. Okay, They are getting generated constantly by planet Earth. Okay. How about gasoline, fossil fuel? Do they get constantly generated? Yes. Okay. We will never run out of gasoline. All right, because it's carbon dioxide. Okay. Oh, all these liberals, environmentalists, climate change, oh, global warming. They don't know what they're talking about. They say those things because they're scientifically illiterate. Okay? Carbon is the building block of life. Carbon dioxide. We breathe out. Okay, you don't want carbon footprint? Then you have to die. Okay? We're breathing out carbon dioxide. All right? And it's not a bad thing. It's a good thing. Carbon is a good thing. Okay? It's a building block. It's like blood of energy. Okay? Blood vessel, all this is currency. It's like money. Carbon is like money. Okay? Plants, they absorb carbon dioxide and they make carbs, carbohydrates. Okay? And then plants, animals eat plants, so we eat carbs. Carbohydrate is like currency. It's like dollar. Okay? Because there's carbohydrate, this long carbohydrate carbon chain, whether it's gasoline or carbohydrate, the carbs that we eat, or the gasoline that our cars, machines eat, it stores energy in there, this chemical chain, through this covalent bonding, okay? Chemical bonding energy, all right? Yeah, so it's currency. Carbon is currency, just like dollars, okay? It's currency of energy. That's what carbon is, okay? Or battery. It stores energy in there, okay? So that's what carbon is, and it gets recycled, okay? So plants, animals, they die, they get buried, and they become fossil fuel, okay? Or lichens and all these microorganisms, yeah, all of them, okay? Yeah, they die, they get buried, and they become fossil fuel. Okay, so you will never run out of fossil fuel. You'll never run out of gold, silver, whatsoever. Okay, because they get constantly regenerated by planet Earth. All right, so there's nothing to worry about. All right, we'll never run out of those things. Okay. Okay. But all this space exploration, that's a waste of energy. Okay, I mean, you can send good stuff like robots to planet Mars, whatnot. Yeah, that's cool. Okay, but space travel, whatnot, that's too risky and it's too much waste of energy. Okay, because yeah, we will have a lot of energy, but don't you have better things to do than wasting all billions of dollars out in the space? You are throwing money out there. What a waste. Okay. Anyways, but recycling is good. Okay, so yeah, we gotta recycle. You know, in the landfill. Yeah, yeah, we should recycle absolutely. All right, let's get back to this. Okay. I cannot think of anything else to say about this. All right, really. It's simple, right? Okay, you have 2, 0, negative 2, 0, negative 2, plus 2. Here is self-sacrifice, altruism, like crucifixion, kind of look like that. And here you have good balance of life. You know, you work and you get the money in. Kind of look like that. And here, you're selfish, like a baby. Baby doesn't work. Baby just sit there, lie there, and acts like a king or queen, right? Oh, bring me the food. Crying is like ordering grown adults, the baby's parents, right? Yeah, bring me food. Hey, change my diaper. Like a boss. If you look at a baby, kind of looks like a boss, right? And if you look at a boss, employers, they kind of act like babies, right? Like so spoiled. Oh, do this, do that. So ordering and so intolerant, just like a baby, right? Yeah, bosses, they act like this immature, retarded child many times, don't they? But they're spoiled, okay? No, nobody corrects them, bosses. What are some quintessential example? President Trump, okay? He's been the boss all his life. Of course he's spoiled, okay? Very immature, intolerant, spoiled brat. That's President Trump, okay? I'm not voting for him again, okay? No. Okay, well, I'm running, so I'm running for president, okay, to replace him, okay? I hope you make the right choice and vote for me, okay? Because, but I may not reach you though. I mean, to be famous on a national scale, that's not easy, okay? So, but I'm trying, okay? I'm trying. All right. Who knows? It may happen. It doesn't matter too much to me. I'm having fun. But I'm kind of running out of topic here. So we talked about this Hooke's law, this spring constant, okay, and also this Foucault's swing pendulum, and they both work the same way, okay? This kinetic energy, okay, and potential energy, spring constant, they work the same way as a sine curve, okay? And maybe we'll do that, okay? We're gonna erase all this because I don't see anything more to talk about, okay? It's so we're gonna maybe we get back to this later, like a month later maybe. Then maybe something will come to us, okay? But our appetite to physics is kind of wetted now. We're kind of salivating over this spring constant like F is equal to kx, that kind of stuff. Hooke's law. We are kind of hooked on physics. I love this pop orchestra. I think it's Royal Philharmonic pop orchestra in Britain. Hooked on classic. Oh, fantastic. Hooked on classic. That great music in YouTube. Oh boy, I love that music. In 1980s, I think. Yeah, fantastic idea. It's combination of the new and the old, pop orchestra. Ah, fantastic. Okay, Hooke's law. So it goes like this. I have this physics book, textbook right here, and my calculus book, it still hasn't arrived. So I contact the seller, hey, give me the refund because you're not sending this to me. So, and I bought from another seller. Now that one is coming. And if that guy doesn't refund it to me, I just let it go because to me time is more precious than money. Okay, so yeah, it's like $100. Sure, whatever. Yeah. To me, money is not that important. Okay, what's more important is time, happiness. So yeah, because yeah, hey, it happens, right? Yes, when it happens, I just absorb the loss. Okay, I don't try to like, oh, I wanna sue you. Contact. contact Amazon so that it destroys your business, expose your evil act. No, I'm not gonna waste time like that. Okay, so, but yeah, people who do that, we need them. Okay, yeah, prosecutors, you know, consumer agencies. Yeah, it's so cool. It's just that I don't have time for that. Okay, I have to move on. So, $100, whatever. Yeah, I asked the seller to return my money, but I'm not gonna do anymore. All right, so okay. Okay, so I have physics book right there, but we're gonna try to go as far as possible without looking at that book. Okay. So you have this wall, and there's this spring. Okay. And you have this floor, frictionless floor, and you have this mass m. Okay. Spring constant k. Okay. So this is equilibrium distance. Okay, but you stretch this spring, or you kind of shrink the spring, then you release it, then it go back and forth, back and forth. Okay, if there is no friction, no air, then we go back and forth like forever. uh, that's the inertia. Okay, just like Earth revolves around the sun forever, right? Inertia. Okay. So if you stretch it out, it will be like, ooh. Okay. Then this distance, we call it x. Okay, the amount of this stretch. Okay, and Hooke, I think that's that physicist's name, Hooke's law, F equal kx. Okay, F equal kx. The farther it goes, the stronger the force is. Okay. All right. Then what is the energy? Okay. Energy is this. Okay. W is equal to F times S. What is S? Space. Displacement. F, um, force. Okay. So that's physics. So F is equal to kx. Let's say this is y. Okay. So then you have graph, right? You have x, you have y, right? So y is equal to kx. It's like this straight line equation, right? And so here you have this triangle, right? The area is, you have y-axis as f and x-axis as distance, displacement, right? So f times s, yeah, it's this integration of, so is equal to integral from 0 to x, f, what is f? Kx dx. Okay, so that's why it is k x squared over 2. Okay, you have kx and you have x right here. What's the area of this triangle? Yeah, kx squared over 2. Okay, so that's the potential energy. Okay, and then it becomes what, the kinetic energy at the center, and back and forth, back and forth. Okay, Yeah, so spring potential energy. It has potential energy stored in this stretchedness of the string, okay, or shrunkedness of this spring. That's the potential energy. Like a frog. Frog is like spring, right? It shrink and then woo. A frog or grasshopper. Yeah, it shrink first, then woo, leap, jump, shrink and stretch, shrink and stretch. Okay, it kind of works like spring. All right, so it's quite has huge application in humanology. I guess we can see it that way. I mean, we never studied spring, this potential energy before in humanology series. Okay, but now it's our first encounter. Hey, nice to meet you. Hello, spring. By the way, I'm not drunk, okay? 'Cause I don't feel like drinking. I drank too much this morning, so soda pop works just as well. All right. Okay, so now it works like the sine curve. You know, sine curve. We're gonna have to derive that, and for that, I may have to look back in the physics textbook because it's been like 20 years since I studied that. Why is it a sine curve? And what are we measuring? Okay, we are measuring x. Okay, I guess it's like time. Okay, so probably the sine curve goes like this. Okay, as the time, right? So at the beginning it was here. Actually, at the beginning it was here, right? So yeah, it's cosine sine. Well, it's just difference by 90 degrees, shifting, parallel shifting along x-axis, right? Probably it is vertical axis is now x, right? So plus x minus x, this displacement vector, right? I mean position vector. Sorry, position vector. So yeah, I was stretching. It was starting right here. So now it's cosine curve, right? Okay. Probably it's like x is equal to cosine t. All right. Now we have to prove it. Okay. This is our hypothesis. Okay. We have to prove that. How can we prove this position vector in time is cosine curve? Well, we may have to solve a differential equation perhaps, or we can solve it in a geometric fashion or analytical fashion. I forgot how to do it, okay? So how to prove this. And we take a break, and why don't you think about it too? Because I probably think about this during the break, okay? Because I forgot. It's been 20 years. For during that 20 years, what have I done for 2 decades? Many different things. 1/3 of those 20 decade 2 decades, yeah, I slept. I was sleeping. 1/3 of that 20 years. So what is it? 7 years? Yeah, I've been sleeping for 7 years. In the past 2 decades, okay. Oh well. Okay, we'll take a break and we're gonna think about this, okay? So can you read all this? Can you see this? Is it too far away? Yeah, you can see it. X is equal to cosine t, okay? We need to prove this. Alright? So yeah, let's think about this, okay? Alright, we'll be back. Okay. Yeah, I mean, if you are good at physics, you probably spotted my error. It's f equal minus kx, okay? Sorry. Because you have this position vector, okay? That's x. Plus x, minus x. When it stretches, we assign this positive sign, okay? When it shrinks, we assign negative sign, okay? Because this is right in the middle, 0, along this x-axis. Okay? So, yeah, it is differential equation, okay? So, now we can erase the 7 hierarchy, okay? Because we are not dealing with that. We are dealing with physics, and we need space. So we can always rewrite it. So, okay. And I'm gonna bring this closer to you because we're gonna write a lot. Okay? We are running out of space. Tripod walking. Eee. Have to re-angle. You don't have to see me. Right? But you do need to see the whiteboard, so. All right. Oh, every square inch is so precious asset. All this kind of space, real estate. We have to be very frugal with spacing, okay? Because we have limited space. So, F equal ma, right? F is equal to ma, and now it is equal to minus kx, okay? What is a? So you have x 2 prime, okay? So it's the second derivative of, okay, a is equal to dx, d squared x, dt squared, okay? Because it's acceleration, all right? So we have nice differential equation right here, okay? Okay, so that's the differential equation you need to solve. And I'm not very good at differential equation. Okay. We're gonna do some guesswork, okay? So, all right. There are 2 possibilities, okay? Okay, you have function x is equal to, is a function of time, all right? You differentiate twice, it kind of becomes itself, okay? Except there's this negative sign, all right? So what kind of function would that be? It's a guesswork, all right? So because again, I'm not very good at differential equation, okay? So I took a class in differential equation, but I audited, no credit, okay? Just as an auditor, audience, all right? And so I kind of fell asleep during that class, okay? So I'm not terribly good at differential equation, all right? So we do some guesswork, okay? So what kind of function would it be if you differentiate twice, then it becomes itself, and in addition you switch the sign, okay? Several possibilities. I mean, several candidates. What if this equation ex is like something like, okay, Oh, what about this? I'm gonna write it in different color. What if, what about this function? X is equal to e to the minus k over m t. Okay? Then x prime is equal to minus k over m e to the minus mk, which is x. Okay, so yeah, it kind of looks like that, but if we differentiate again, then it flips the sign again, so that's not gonna work. Okay, how about some what trigonometric function? So yeah, so this one doesn't work. Okay, so yeah, so this exponential function, you know, what is e? Euler's number is this. Okay, e to the x, you differentiate it, well, e to the t. Okay, differentiate it, it becomes itself, e to the t. Okay, so that's kind of definition or characteristic of this number. Euler's number is irrational number. It's like 2.73 blah blah blah. Okay, so yeah, exponential function. Okay, so yeah, that one failed, so that one didn't work, so we don't need that anymore, so we're gonna erase that. Woo! You have to erase that on kind of mini eraser at the tip, but yeah, let's try trigonometric function, and let's say x is equal to minus k over m sine t. Sine t, okay? Let's differentiate. X prime is equal to without negative sign, okay? X prime is equal to m over k over m cosine t, okay? X2 prime is equal to minus k over m sine t, which is x. All right, so what if x is just sine t without those constants? We're getting very close, okay? I suck at mathematics. Oh boy. I really suck at this. Oh, I'm sorry. Oh. I should have I should not have fallen asleep during the differential equation class. Ah! Man. We are getting very close though, don't you think? Oh, it's just this freaking constant. That's what we are struggling with. That's what I'm struggling with. Hey. But you got the idea, okay? I'm trying to run away from this deficiency in my knowledge. If you are engineer, if you studied like some kind of engineering and took some differential equation, you may be laughing at me now. Oh, idiot. Okay, how about this guy is like inverse of that. Yeah. How about what if we define x as m over k, m over k, m over k, minus m over k. Son of a b. I'm sorry. Sorry. Okay, so that's minus x. So what we are trying to do here is we want to define x as a function of t so that it satisfies this differential equation. Okay, that's what we are trying to do. All right, we want to find that x as a function of t where we differentiate twice and then it becomes kind of itself multiplied by minus k over m. All right, that's what we are trying to do. What if what if x is equal to sine square root of km times t? How about that? Okay, well, then x prime is equal to square root of m k cosine. It's a chain rule, okay? We're doing chain rule here. And then x2 prime is equal to, can you see this? Yeah. This guy come out again, right? So, and you have negative sign. Now we have k over m sine. Okay. We got it. We got it. We got it. Yay! And this guy is x, which is equal to minus k over m x. Okay. Yes. Yes. We got this equation. Okay. So yeah, it's like it's sine, cosine. Yeah, it's not that important. All right. Because why? Because cosine curve, cosine t is equal to sine goes like this. Okay, so it's a sine curve is like this, you know. So you shift it negative. So t plus pi over 2, which is 90 degree. Okay, that's so yeah, cosine sine, they're kind of equivalent. All right, so it's just constant difference. You shift it negative 90 degrees, then sine curve shifting negative 90 degrees, then it becomes cosine. Okay, so yeah, it's a sine curve. Okay, it satisfies this differential equation. All right, so yeah, we got it. Oh boy, it took so long. Okay, so yeah, it's sine curve, cosine curve, same thing. Okay, so we just proved it. Okay. Whew. So it's like this life of a frog or grasshopper, right? Shrink its hind leg, then stretch, shrink, stretch, like push up, sit ups, right? This sine curve is very important in humanology because it's like everything, circle, right? In Buddhism, probably the most important figure, geometric figure, is a circle. Okay. There's this very famous Korean Buddhist monk. He wrote many books, and he also studied some physics. So yeah, Buddhism is kind of like Christianity. Okay, they do this lecture, preaching, okay, sermon. So when the big Buddhist monk, very famous in South Korea, when just before he passed away, he drew a circle. Okay, so basically a circle of life. Yeah, so circle is probably the most important geometric figure in Buddhism. Okay, and in society, maybe in sociology, or even in Christianity, probably the most popular geometric figure is what? Probably triangle, right? Yeah, society, food pyramid, that kind of stuff. Okay. Yeah, we do that too here in humanology, right? Especially in economical humanology. Yeah, we use a lot of triangle stuff, but now we are doing circle. Okay, circle of life, night and day, night and day. You sleep awake, circle, eternal circle. Okay. Yeah, Friedrich Nietzsche, he talked about eternal recurrence. Okay, but he got it from Buddhism or Hinduism, like Rig Veda or Upanishad, whatnot, right? Yeah, he got that circle concept from Buddhism. Okay, Indian philosophy or Chinese philosophy. Okay, so yeah, circle is very significant in ancient philosophy and religion. Circle of life. Okay, so yeah, it was worthwhile to do this mathematical exercise. Okay, because we just proved that yeah, it's very circular. Just because I love you, I'm gonna show you just one last time why a circle is this trigonometry. Okay, because we did this several times before. Okay, but just in case you don't know enough mathematics. Okay, and if this is all confusing, we'll step back and explain it to you, okay, after a break, okay? But we'll take a break and we'll get back to this, all right? We'll do some trigonometry basics for you, okay? All right. Okay. So we're back, and uh, yeah, we're gonna erase this, and we're gonna do some basic trigonometry, and after that we do pendulum, all right? Like pendulum of politics, Democratic Party, and then Republican Party, you know. Pendulum. You go left, right, left, right, left, right, just like marching, right? You know, U.S. Army. You know, left, 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 right, left. You know, cadence. Oh, good old days in the army. Yeah, you go left and right. Some Democratic Party candidate become president, and then next time, Republican Party. It's just pendulum, you know, political swing, or even society. One time, society is kind of like liberal, and for a generation maybe, or for a decade, and then next decade become more conservative. Yeah, pendulum swing. But before that, I'll do this trigonometry for you, okay? One last time. Okay? So it's like this. You have x, y, okay? And you have circle, okay? And you have this clock, hand over clock, okay? And in mathematics and physics, clock goes counterclockwise, okay? Counterclockwise. Because this is time, and also it's an angle, okay? Theta, t, okay? And the radius of the circle is 1, okay? And what is this? X. X is equal to well, before that, what is cosine t in trigonometry? Cosine t, you have hypotenuse, okay? T is angle, okay? Also is time. Hypotenuse goes to the denominator, like cosine, okay? You have triangle, right? Cosine. The hypotenuse of this right triangle goes at the denominator, and then you have this base, okay? Let's say you have hypotenuse, base, and height. We just call it A, okay? Yeah. Cosine, this is theta. Theta is equal to H goes below, and then B goes on top. What is sine t? It's like how do you write sine? S like ooh, something like this, right? So that's sine, okay? Sine theta is equal to H go at the bottom, and then you go on top. You have A, okay? So it's by definition, all right? How did they name sine and cosine, tangent? I have no idea. Okay. How about tangent? T, right? Ooh, ooh. Tangent t, tangent theta. B goes at the bottom, and then A go on top. Okay, so it's by definition. All right. It's the ratio between different sides of a right triangle. That's what trigonometry is. Here, cosine t, you have hypotenuse, and then you have base. Okay, so x is equal to cosine t. Okay, sine t is equal to 1 goes down, and then you have this y. Okay, that's coordinate of this point on this circle. Okay, so y is equal to sine t. All right. How about curve? X is a shadow of this hand of this clock that goes counterclockwise. All right. As this hand of this clock goes like counterclockwise, you shine this flashlight from above. Now X is the shadow. Okay. So now we have this t-axis. By the way, can you see all this? Yeah, it's orange color because I love color orange. It's kind of too light, maybe. Can you see this? Let me see if you can see it. Yeah, you can see it, right? Is it too far away? I'm sorry. I bring it closer to you. It's not that better, but it's just elementary, okay? So I just start writing in black or brown. Brown goes better with this. Brown is better matching with the orange, okay? So, really like color matching, okay? My necktie and suit, my pants. Yeah, I like color matching, okay? So, all right. So, in okay, now y is shadow on the wall. So x is the shadow of this clock hand on the ground, on the floor. Okay, you shine the light on top of this clock needle with a flashlight. So x is the shadow. Okay, kind of on the ground. Y is a shadow on the wall. Okay, now you have flashlight from the left and you're shining the light from the left to the right, and the wall is on the right side. So y is the shadow of this clock on the wall. Okay, it's called projection. All right, so we'll do y. Okay, so what is y? Sine t, right? So time, okay, is horizontal axis. Vertical axis is still y, okay? When time is 0, angle is 0, right? So it's right here. When time is right angle, like pi over 2, okay, radian angle system, okay? If you are not familiar with pi, 2 pi, it's like this. What is pi? 2 pi, pi over 2 is this, okay? You have circle where the radius is 1, okay? The circumference of this circle is pi r, 2 pi r, right? So yeah, circumference is equal to 2 pi r, and r is 1 radius, so it's 2 pi. So radian system is nothing but this length, arc length, which is proportional to this angle, okay? So radian system, radian angle is nothing but arc length of a unit circle. What is a unit circle? A circle whose radius is 1, okay? So 2 pi is 360 degrees, okay? 180 degrees, that's pi. 90 degrees, pi over 2. Okay, that's the length of this arc. Okay, that's the radian system, all right, of angle, to measure angle, okay? In case you don't know, all right? Because I want you to know mathematics, all right? So, well, so when t is 0, this shadow length is 0, right? When t is pi over 2, then the length is 1. This is a pi over 2. When t equals pi, then the shadow of y is also 0. When t is equal to pi plus half a pi, 3 over 2 pi, 1.3 pi, then the shadow is now downward, right? So negative 1. When pi is, so this pi, 3 over 2 pi, and when pi is equal to, when t is equal to 2 pi, then yeah, it's again, it's completing the circle. So yeah, this is sine curve, okay? All right? Goes on and on and on. Okay, so that's what sine curve is. I'm just giving you basics of trigonometry, okay? So, good. I'm getting really overheated now, so I'm gonna take a break. And I'm gonna grab a drink, okay? Because, oh, it's getting too hot. Okay? And we'll do the pendulum, where we'll derive formula why pendulum is also sine curve. Okay, we'll do that next after a break. Okay. Oh, it's getting too hot. Okay, we're back, and my house cooled down a little bit. So that's good. I'm gonna take off this jacket because until I get cold again. Okay, so um, oh boy, oh it's hot. And also I have two layers of pants and sweatpants. Do you mind if my pants is red? It's like it's not pink. It's just kind of magenta kind. Anyways, yeah, let's erase. We'll do a little bit. We'll take a break from trigonometry. Okay, we'll do a little bit of different function. Okay, we'll do exponential function. Okay, because we just mentioned e to the x, right? How about just general, like general stuff, like 2 to the x, a to the x, exponential function. Okay, because try to remember what's the differentiation of general exponential function is. I think dy dx, I think is something like ln a times ax. That's what I think. I know it's ln a goes somewhere. Is it in the denominator or numerator? I don't remember. Okay, let's see. Or let's cheat. Let's look it up in the internet. Ah! I don't want to do all that. I don't want to spend too much time in differentiation. Okay, I just want to recall. That's all. Probably I'm not gonna forget it. If even if I don't derive it, I just look it up. And differentiation of exponential function. Yeah, ln a, that's what it is. Okay, that's it. Okay, that's all, what we're gonna do. This is correct form. So ln e is log e to the e. So that's what is ln? Logarithm function is, okay, it's just inverse function of the exponential. X is equal to logarithm of a base a and y. Okay, so that's what logarithm is. It's just your function. Okay, you have an exponential function that goes like this, right? Logarithm function is nothing but reflection on this function y is equal to x. That's logarithm function. Okay. Okay, very slow growing function. You have asymptotic line, you know, it infinitely approaches, get closer, closer, and you have asymptotic line here, get closer and closer, closer. Okay, so this is logarithm. Okay. What is ln? Log natural. Okay, log base e to the a. Okay, times a. Okay, so that's what ln is. Okay, log natural. All right. Yeah, some mathematics. Okay. So if y is equal to e to the x, then ln e log e to the e, that's just 1. So that's why. Okay. Yeah. So I'm just giving you some basics. All right. So mathematics. Now let's do pendulum. Now we are ready to discuss pendulum. All right. Okay. Why is pendulum also sine, cosine, trigonometric function? So maybe like this. Probably this one's easier, okay? Because we're gonna do some geometry. I don't think it will involve solving a differential equation, okay? So your pendulum, okay? I mean, you have ceiling, right? You have string. Now, pendulum swings back and forth, okay? Math M, all right? Boy, maybe it's not that simple, huh? Ah, boy. Yeah, so here the force is gravity, of course, right? F is equal to, now we have gravitational acceleration, we call it G, okay? F equal to ma, acceleration now is G, right? So that's the force that's try to bring this pendulum down. That's force, okay? Boy. And it will come down here is in a circular fashion, right? Because you have fixed the radius here, right? We call it R, okay? And then you go to the right, right? Yeah, a circle, part of a circle. Just pretend this is a circle, okay? All right. Radius R. I forgot to grab my drink, so. Now, what is significance of trigonometric function here? Ah, man. It's been such a long time, so I have to think about this because it's been a long time, okay? It's been a very long time, so oh boy. Yeah, we'll start with this. We'll try to use blue, okay? It's not the best matching of color, but let's say this is X, okay? From here to here, this position, okay? Let's say this is X, okay? So you start from here. Start from the right and left, right, left, right, left, right, okay? Okay, so we have theta, and what we want to find is we are suspecting, okay, X is something like sine t, okay? Something like that, okay? Sine or cosine, whatever, right? That's our guess. Because differential equation, I think it's kind of art, okay? I don't think they have like generic formula for the differential equations. It's an art, a technique, kind of heuristic, kind of guess game, whatever. Okay, so we just take a guess at it. So whew, phew. How do we go about solving this, man? Oh boy, pendulum. Oh, pendulum conundrum, huh? I have no idea. Okay, oh boy. When we did the spring, we have that F equal ma, right? Because and that force was kind of proportional to the differentiate the position vector. So yeah, F equal ma is equal to kx minus kx. Okay, that's what we did. But here, oh boy. I guess we have this, perhaps we have to analyze this vector. Like you have tangent vector, right? So you have gravitational force pulling it down, and this string tension force that's pulling it up. That's why this ball at the end of this pendulum is kind of in the air because it's balanced. Force pulling down, force pulling up, this string tension force. Yeah, it's in balance. That's why this ball is kind of in the air, floating. Okay? It's a balance of two different forces, pulling it down or pulling it up, so it's kind of in the middle, you know. And but because it's angled in this situation, now we are doing vector summation of these two different forces. So it's going that way. Okay? Man. What did we get ourselves into? Oh boy, this I thought it would be a lot easier, but it turned out to be more difficult than this spring equation. Our guess is that this x is sine some trigonometric function because it's going back and forth. No? That's our guess, and now we probably have to come up with differential equation again. Okay. Well, here the t is not equal to theta, okay? Because time is always positive, but theta here is positive and negative, positive, negative, okay? But all we know, x is equal to, let's say this r is 1, okay? Then as x is equal to sine theta, right? With this r, we just give it 1, okay? 1. Radius is 1, okay? Then yeah, x equals to sine theta, all right? We know that much. Is this enough? No, we want to express x as a function of time. Okay. Oh. Boy. And this angle, okay, you circle, right? And actually, this direction where it's going is tangent to this circle. So this has to be right angle, okay? And I'm suspecting this angle should be theta, okay? Let's see if that's true. Or theta minus 90 degrees. This should be 90 degrees minus theta, I think. Why? Let's see why. Okay, so you have, yeah, it is. Because this is theta, right? In geometry, you have two parallel lines and one light going through it. So yeah, this should be theta. So yeah, 90 minus theta. Okay, we're getting close, I think. Okay, so, oh, okay, so. And this tangent force actually is opposite direction to this. Okay, now we are getting close. Okay, because and we have 90 degree here. Okay, so we are now analyzing this force vector into two different directions. Okay, what is analyzing over vector is kind of a reverse process, reverse engineering of summation of two vector. Okay, so you have x and y axis like this. Okay, and you have vector, right? Let's say vector A is equal to, let's say this is B and C, okay? You are analyzing vector A into two vectors, B plus C, okay? This vector analysis, okay? That's what we're doing here. You have vector, this gravitational force downward, and you are dividing it into two vectors, tangent and this tangent, okay? All right. So this tangent force, tangent vector, this we call it Ft for tangent, okay, is equal to um, F gravitational vector is this sine or cosine? Probably sine. Because you have a 90 degree angle here, okay? So sine theta, okay, is equal to Fg go down and then here, Ft goes up. Yeah, it's a sine theta, okay? This is tangent, same as tangent vector, okay? I'm sorry, the diagram is not very clear, but okay. So that's that. I hope you are following this, but probably the preliminary is that you took some science class, mathematics class, then you'll be able to follow what I'm doing. Otherwise, it may be too fast. But we are just doing this for fun, okay? Because we are in the realm of humanology. We are not doing physics. I mean, we do it for fun, okay? So it's not our purpose to teach you physics because our goal is to use physics for humanology, okay? So I cannot give you all the details of this, all right? So we don't have time, all right? So yeah, please look up the in the online dictionary, I mean online web page about physics, pendulum, mathematics, okay, trigonometry, and catch up, all right? That's all I can say. All right, so yeah, we have that. Now what? Hmm. Okay, we have tangent force, and then we have this string force. Okay, we call it uh, string force. All right, because we cannot call it tension force because we have already this tangent force. All right, Fs equal to Fg cosine theta. Okay. Well, minus because it's in the other direction. Okay. I'm sorry if I'm waving hand too much, but now what? Oh, I may have to look at the physics book, okay, because it's taking too long. Taking longer than it should. All right, we should not spend too much time in physics or mathematics because we are doing humanology here. All right, so okay, so I'm gonna look at this physics textbook and look up pendulum in the index and see how they derive what kind of differential equation they use to have expressed this position x in terms of time. Okay, pendulum. Let's look at the pendulum. And what is book for? If we are not losing it, using it. Okay. 436. Pendulum. All right. So yeah, we got sine theta, cosine theta. Yeah, we got that. Hmm. Okay. All right. Okay. Oh boy. All right. It turned out that they're cheating too. The oh, they're cheating too. Okay, so the way they cheated is like this. Okay, so they're doing approximation here. Okay, um, they say when this this angle is very small, uh, okay, there's this famous equation in mathematics where limit theta is go to 0, x sine x is equal to 1, meaning you have this, can you see this? You have sine curve, right? Sine curve. And you have function y is equal to x, right? When x is very close to 0, they are very, very same. Okay? So, it's a famous equation. Just please don't ask me how to approximate this. I have to prove this. Well, it has to do probably with Taylor expansion, I guess. Okay, so, okay. Yeah, so that's that. Okay, so, and also there is another equation where you have a circle, right? And this is R, and this arc L, you have theta, right? L is equal to R times theta, okay? When theta is in radian system, okay? Why? Because the longer this theta is, this, and the bigger the theta, this radian angle is, and the bigger this circle's radius is, yeah, the longer the arc length becomes. Okay, so L equal R theta. All right, because arc length is just a part of this big circle, right? So you have this equation where 2 pi theta is equal to 2 pi r L. All right, so 2 pi cancels L equal R theta. Okay, so it's just direct proportionality. All right, so they're using that. Okay, in this physics book, so they're using that. All right, so and then when theta is very small, okay, so you have this Foucault's pendulum where this you have this huge, like very long cable, metallic cable, right? And so this R radius is very big, okay, and then you are just Foucault's pendulum, you know, to keep this theta very small, you know, and if that's the case, if that theta is very small, then this tangent force by the way, now that we assign this direction, okay, this is x direction, right? So we gotta switch some signs here, all right? So this tangent force, okay, and we have tension force too. So when theta is very small, this tangent force is nearly horizontal, okay? So and also Fg, you have Fg and you have sine theta, okay? And we should have done it from here, okay? Because here we assigned this as positive theta, okay? But we did it here, so we should put negative here, okay? Because tangent force, because sine theta, yeah, here theta is negative, okay, and the tangent force is like toward the x direction, so Negative times negative is positive, all right? So yeah, we have to do that. Okay, so we have a situation where this tangent force is equal to minus what is Fg? Ma, right? Ma times theta. Okay, it kind of looks like minus kx, right? Why? Okay, what is x? X, when theta is very small, as x is very close to this arc length, okay? When theta is very small, like this x is very close to this small arc length. All right? So that's what they are doing here in the physics textbook. Okay? They're doing a lot of cheating, a lot of approximation. Okay? So when theta is very small, all right? When theta is very small, this arc length, what is this arc length? X is equal to r times theta, right? That's what we did here, okay? So this becomes minus m times a mg, sorry, mg times r theta is equal to x over r. All right. So we have this ft is equal to minus mg over r times x, and we can put this guy as a k, some constant, okay? Then we have f is equal to minus kx, just like in the spring, all right? And we apply the same differential equation, and then now we have it. Yeah, so they call it harmonic function, okay? Harmonic function. Yeah, it's a. So yeah, we got it. Okay, so I had to look up this physics book because yeah, they cheated too, so I had to cheat as well. Okay, because they use this small theta and they use this equation. Okay, and I could have never come up with that because we got it. Okay, so we have 1 hour left, and now we'll talk humanology. Okay, because I'll leave it here before I erase and before going to break, because why don't you mule on this? Okay, yeah, look it up, catch up. Okay, enjoy. All right. I'll leave this to you. All right, and we're gonna take a break and we'll be back. Okay. Okay. Oh, that was long, but we got it. Okay. So. Oh, it took so long. Okay, we're not having very nice and cozy Saturday evening. Okay, so now I'm gonna erase this, and we will do this humanology thingy. I'm not sure what this harmonic function, whatever. I don't know quite how we, yeah, vicissitude of life. You know, life going up and down. Uh, isn't What about it, man? Is it kind of commonsensical? I mean, is there anything intellectually interesting about it? Maybe. Okay. Yeah. How about suicide prevention, huh? Because we talked about suicide briefly. Okay. Let's say I'm dead, and people are wondering, did he commit suicide? How did he die? Oh, you're so lonely. Oh, loser. Whatever. Do people who die from suicide, do they go to hell? Well, we don't know. Okay. That's God's job, not ours. Not ours. Okay. So, I mean, it happens, right? It's no joking matter, of course, because there are loved ones who lost their loved ones to suicide. It's a suicidalism. Okay. It's a evil ideology. Okay. Very destructive. Okay. They're just victims of the bad ideologies. Okay. We can talk about afterlife very briefly. Okay. Afterlife. We don't know too much about it because it's hidden from us. Whether it exists or not, we don't even know. Okay. We don't even know whether afterlife exists or not. Okay. It's Zoroastrian, Zoroastrianism. Probably they came up with the idea, and Jesus kind of learned from Pharisees. Who are Pharisees? Like Persians. Yeah, Persia, right? That's where Zoroastrianism came from, right? So yeah, I think Jesus was heavily influenced by this Zoroastrianism because I read an article about that, and I think they make sense. Okay, because all this heaven and hell afterlife concept didn't quite exist in the Old Testament. All right, they talk about afterlife briefly in the Old Testament, like once. Okay, but okay, there's this King Saul, right? And Prophet Samuel, he died, and when King Saul was also, when Saul was still king, so he went to this sorcerers and summoned up this dead soul of Prophet Samuel. Okay, yeah. So obviously, Prophet Samuel was still living after he died in underworld or afterworld, afterlife, right? That's all Old Testament talks about in terms of afterlife. Okay. Old Testament does not talk about heaven and hell. Okay, that's probably came from Zoroastrianism that Jesus learned from Pharisees. Okay, Persians. All right. Yeah. So that theory makes sense to me. Okay, I read it in the internet. Okay. So so yeah, suicide prevention. Okay, so ups and downs of life. It's a sine curve, right? Why is it sine curve? Let's try to see that. We just derived this nice sine curve cosine formula, you know, by solving this differential equation, right? Yeah, let's do something like that. Why does life go up and down? Why is it a sine curve? Okay, we will have to come up with a humanological differential equation, maybe. Okay. I don't even know where to begin. Okay, so because again, I'm not good at differential equation. Okay, so so How do we go about it? I have no idea. I don't know. All right. Oh. What we do know is this, all right? If you have lived long enough, you know, just by experience, okay? Just by experience. Let's keep it simple, shall we? This is time axis, okay? Y axis, how about happiness? You have highest point, okay, and you have some middle point, right? I'm just comfortable, right? Uh, can you see this? Is it thick enough? Um, do I have some different color? Yeah, I think this is good enough. Yeah, you have high point in your life when you're very happy. Just look back in your personal life history, and you have very low point in your life. And then, just looking back in your history, life history, you have also a high point too, later on in your life. So yeah, it kind of like sine curve, okay? Just like night and day, okay? So that's what Solomon says in the book of Ecclesiastes, I think, or Proverbs. When you hit the lowest point in your life, just remember, it will get better. It will get better. Things will get better, okay? And he also says, King Solomon says, when you are in the highest point of your life, be aware that it's not gonna stay there very long, okay? So yeah, be on guard, okay? Don't be complacent, okay? Yeah, you need to save money as much as you can, rainy day fund, because things will happen in life. You will need more money sometimes, right? What if you get injured, What if you get fired? Or what if they lay you off because the company you work for is not doing very well sometime in the future? So you didn't do anything wrong. It's just economic cycle, right? Yeah, they may lay you off, let you go because they cannot pay you. Yeah, I mean there's unemployment insurance, but it's not enough, right? So you may have to live off of your savings for a while before you get a new job, right? Yeah, by all means save. I try to save as much as I can, okay? But I'm not good at it. Okay. At the same time, you don't want to save too much, right? Why? Because think about it, you can die tomorrow. Then where does all that money go to? I mean, you cannot take the money with you to afterlife, okay? So yeah, you may as well enjoy while you're alive, right? So strike some balance, okay? Save some, use some. Okay? We just leave it at that, all right? Yeah, when you hit the lowest point, yeah, don't commit suicide, okay? Because things will get better, okay? No matter what problem you have, you can overcome, okay? So, okay? What time is it? 9:30. I'm thinking I may go to a bar tonight, okay? Because I'm not sure. Yeah, so I'm kind of bored here. Uh, Yeah, it's up and down. Happiness level, yeah, it go up and down, okay? And all right. And now let's think about um, some different perspective in human life where you have night and day, you sleep and awake, right? Um, it's a, life cycle. And what about it? I mean, it's something too commonplace, so it's not very interesting or exciting. But I'm kind of lingering on. Maybe we can find something. You know what? Let's look at the physics books, okay? Let's look at physics book. Maybe we'll find something there. This, what page was it? Something 436 or something? Periodic motion. Good. Oscillation. Yeah, you have the spring. Simple harmonic motion. Okay. Good old days. Physics. Okay, there's this diagram of kinetic energy, potential energy. Okay. Ah, beautiful stuff. Ooh, beautiful, beautiful. Damped oscillation, resonance. Okay, okay. Pendulum, spring. Okay, potential energy and kinetic energy. Maybe that's what we're gonna do. Okay. In simple harmonic motion, you have this potential energy and kinetic energy. Okay, so let's just do this spring. Okay, so this pendulum. Oh boy, it's too many cheating approximation. Oh, too complex, right? Yeah. So you have energy is equal to kinetic energy plus, well, potential energy plus kinetic energy. Okay, like free falling uh, well, we can erase all this sine curve here. Okay, sinusoidal curve. In a free falling body, right? You have B. Woo. Here you have this H. This is the ground level. Okay, H. So initially it looks like this. Okay, it's something I learned in physics in high school. Okay, something like maybe it's not straight line. Maybe it's a parabolic line. Whatever. Okay, but just to simplify. Okay, kinetic energy. I mean potential energy on top, yeah, it was all potential energy, okay? But as you go down, yeah, now you have more and more kinetic energy. What is kinetic energy? So this guy, potential energy is what? M, G, H. Kinetic energy is 1 over M, V squared, okay? Why? Why is it mv squared? It's integration, okay? F equal ma, right? Energy, okay? And energy W is equal to F times S, okay? So it's like M times A times X, something like that, okay? So now, what is MA? Boy. It's like this, okay? You have so this is X and this is ah, why is the kinetic energy mv squared over 2? It's because it's been such a long time, okay? E. Because we have constant force, the gravity, and we have constant acceleration, okay? So v is increasing, okay? And acceleration, oh. So it's basically it's a line integral, okay? This is a integral of f times f and dx, okay? It's a line integral, all right? So what is f? So w is equal to m times a dx integral something like that. Oh boy, man, I used to know this, okay? I'm sorry, I'm so lost. Let me look at the physics book, okay? How they derive this kinetic energy formula. Kinetic energy. Oh boy. Ugh. Energy kinetic. How about that? Energy kinetic. Kinetic energy. $181. Okay, so it's early on. How long is the book? 1,400 pages. 181. Kinetic energy. Okay, it was not that simple, huh? Sure. Okay. Okay. Boy. All right. We have only 30 minutes left, but we can continue after this. Okay. I got nothing else going on, so. Okay. Okay, I'm kind of getting it. All right, so wow, it's so involved. Okay, so oh boy, let's go back to the basic. Okay, so we are moving a particle. Okay, with mass m. All right, and there is some kind of constant force. Okay, so there's constant acceleration F equal ma, right? All right, along the x direction. All right. Whew. So v is equal to v0 plus at, right? S is equal to, it's just integration, okay? S0 plus v0t plus, it's just integration, simple integration, okay? Of 1/2 at squared, okay? Okay. And a is equal to just a. So you integrate this in terms of time. Then you come here, you integrate again, then you come here, okay? So integration, and the other way, differentiation in terms of t, okay? Differentiation. Integration, differentiation, all right? So, oh, okay. We have a, okay, boy. So we have v and v0, right? And you have here mv squared, right? So we have to get rid of t, time, okay? It gets really messy, okay? So s minus s0 is equal to v0 times v minus v0. Oh, no, sorry. What is t? T is from here, v minus v0 over a, okay? That's t. Plus t squared. Oh boy. v minus v0 over a squared, okay? Oh boy, it is. So s minus is that delta s, okay? Delta s times 2 is equal to v0, v minus v0, that's delta v, right? My plus, well, over a. Now a squared at the bottom, so now you have a delta v squared, okay? So You have 2a delta s is equal to delta v, v0 plus delta v, okay? Oh boy. Did I make some mistake? Yes, I did. There should be 2 here. Okay? There should be 2 here. All right? I'm sorry. So, here, yeah, we have 2 here, 2 there, so 2a delta s is equal to v2, what is delta v? v2 minus v1, all right? Multiplied by, now you have 2 v0, and here v, you know what? I'm not going to confuse you, okay? So we have v is like v minus v1. So v is the second velocity. v0 is the initial velocity, okay? Now you 2v and you have v minus v0, so v minus v0, so it cancels out, so v plus v0, okay? Right? So you have that. Now we are getting very close. We get back to this diagram later, okay? But for now, we gotta finish this. I don't like memorizing. I want to understand, right? So I want you to understand too. Don't just take the result. Don't just follow the hard. Yeah, get to the bottom of it. Try to understand, because people can be wrong. Like economics, for example, they have this Alfred Marshallian supply and demand curve, and we disproved it. Okay, 100 years later. Okay, so yeah, let's doubt, just like Rene Descartes, right? Okay, so now you have delta S is equal to here v squared minus v0 squared, right, over 2a. Okay, now what is work? F times delta S. Constant force, you have some displacement, okay? What is F? M times A, right? Okay, what is delta S? V squared minus V0 squared over 2A. So multiply by MA, you have we got it, okay? So yeah, constant force, so constant acceleration. So you have V0, initial speed, and second speed, V, okay? In this situation, yeah, we call this just kinetic energy, okay? So that's where this comes from, okay? Oh, we got it. What is why F is mg, right? S h, free falling body. Okay, so yeah, every coordinate. So we got it. Now, so it took so long. Sorry, but just the way it is. Okay. So free falling body. Okay, free falling body. We can just put this heavy, good physics textbook away. Oh boy. I mean, as a side note, when I was a college student, man, oh boy, we have this heavy textbook, right? So it was okay, why? Because we are young, college student, right? So we have this backpack carrying these heavy books. It didn't break our back because we are young, you know. So, but when I went to law school, we have heavy books too. What did I do? Because I was old. I was like 35 when I went to law school, you know. So I chopped down this textbooks like chapter by chapter, so that I don't have to carry all these other chapters. Of course, I don't get to resell my books, but well, I never sell my books anyway. When I move out, I just dump all the books in the dumpster. That's what I do. Too much work, okay? To resell, I have to find the seller. I have to put it in the internet, and forget it, okay? To me, time is more precious than money, okay? My life, I want my life, you know. Money, I don't need money. I just get to pay my bills, and that's it. I don't need any more than that. I need time, you know? Time to enjoy my life. Freedom, you know? So yeah, money can devour your time, okay? So if you're focused on money, you lose your time, your happiness, your freedom, because you're working for money, okay? So yeah, this is just an anti-mammonic rule. Yeah, you cannot serve God and money, mammon. Yeah, it makes sense, okay, actually, okay? So you cannot have both freedom and money, in a sense, okay? Because if you work for money, if you want to get a lot of money, you have to work a lot, then you don't have free time, okay? Me, I work just 40 hours a week, that's it. Yeah. Because I want my freedom, free time, all right? So that's that. All right, we have like 15 minutes left in this episode, and we may continue, okay? We may continue. So kinetic energy, free falling body, you hold this ball and you drop it. Ooh, bang, on the ground level, okay? So at the beginning, you have this potential energy, right? EP. It was standing still, so kinetic energy was 0. At the bottom, all you have is kinetic energy. This is speed, you know. 1/2 mv squared, okay? So yeah, conversion of potential energy to kinetic energy, okay? Now, you have spring, okay? And we already have covered this before. What is a potential energy? Well, Fs, right? And F, the force increases as this position vector increases. So potential energy here. So in the spring, if potential energy is 1/2kx squared. Okay, what is kinetic energy? Well, same thing. half mv squared, okay? So that's kinetic energy, okay? At either end, when spring is very stretched or spring is very shrunk and compact, okay? Yeah, the kinetic energy is zero, okay? So yeah, I just saw this diagram where kinetic energy is zero, okay? So kinetic energy is maximum when it's in the middle. The spring is in the middle, okay? So this is E kinetic energy, okay? The rest is potential energy, okay? Potential energy is maximum in on this either end, okay? It's potential, you know? It's not moving because at this point, velocity is zero, okay? Because it's changing direction. It was going this way and then this way. So plus, minus. In the middle of plus and minus is zero. At this point, it's static. There's no velocity, okay? Maximum potential energy there. It's like this, okay, in life, okay? When you are not doing anything, when you're sleeping, resting, you're storing energy, potential energy, okay? Then you start moving, and now the kinetic energy is maximum. Okay, you're going toward this maximum kinetic energy where you're doing something, your activity, you have some velocity, you know. But if you're at a static level, when potential energy is maximum, you're not moving. Velocity is zero, right here. Okay. You can see this as a ball. You drop a ball, like basketball, it kind of bounces around. Okay, if there is no air, it's a vacuum. Okay, you drop a ball, it will bounce like this forever and ever and ever, okay? Because there's no friction. Okay, and let's say this ball somehow does not make any sound. Okay, so there's no sound energy either. Okay, yeah, it will bounce back and forth forever in a vacuum. Okay. Again, simple harmonic motion. All right. Yeah, we can derive some equation with that. Okay. Why don't you? Yeah, because I don't want to go back there at this differential equation. Yeah, dropping a ball. Okay, bouncing back and forth. I guess we can do real quick, right? F is equal to what? F is equal to what? Mg, right? I don't know. Okay, it's just it will bounce forever like this. Okay, I'm kind of being tempted to prove that this is simple harmonic motion. In the vacuum, you're dropping a ball. Okay, so F is equal to mg. Okay, and then you have this y. Okay, so this y-axis go like this. From 0 to h. Okay. Oh boy. We probably continue to the next episode right after taking a break. Okay, we have 8 minutes left before this episode ends, and we'll just keep doing this because it's fun. Okay, now you have the s is equal to s0, which is zero. Okay, plus v0t. V0t is where v0 is zero. So plus 1 half gt squared. Okay, that's the displacement from 0 to whatever. Okay, okay. But once it hit the ground, it will go back up though. Okay, so constant force, and this is s, so this is st. Ooh. Having fun with mathematics and physics. Because I've never seen this kind of equation, I mean this kind of scenario in physics book. Okay, you're in a vacuum situation. Vacuum, there's no air, no friction. All right, and you drop a ball, it will bounce back and forth. We want to prove that that's kind of sine curve, this simple harmonic motion. Okay, that's what we want to prove. Okay. Well, in spring situation, we have F is equal to minus kx, right? And by the way, this is kind of a deja vu. I think, yeah, I've seen something like this. It is equal to mx squared, okay? I mean, m2 prime, mx2 prime, okay? Here we have F is equal to mg. Here F, the force changes, right? But here, force does not change. Okay. Force is actually constant. So it will be different equation from this spring situation. I want to do this because I don't think maybe it has never been done before, or maybe he has done, but has been done, but I haven't seen it. All right, it's kind of challenging, so we like challenges. Okay. Well, let's just start writing down equations because in mathematics you don't want to think too hard. You want to be more mechanical. Okay, so total energy EP plus EK is equal to what? mg y. Let's say this is ground level. Okay, ground level. Okay, this is h. This is y-axis. Okay, we have like 1 minute and 30 seconds, but we keep doing it. Okay, because my voice is doing just fine. mgy, okay, plus m v squared. Now what is v? V is equal to v0 plus okay. So what is v0? 0. Okay, so wow, it's like woo, we have this fourth order here. Ooh, this is fancy. I've never seen anything like this before. This is something. Time is up. Okay, so we're gonna take a break and we continue on this because this is fascinating. Okay, maybe we are making brand new physics theory. Okay, sure, why not? All right, we'll be back. Okay, bye.